In examples 11 and 12, we're going to put all of the information about limits that we've talked about and continuity that we've talked about together, okay? So for example 11, they want you to draw a graph of a function on the interval from -5 to infinity with the following characteristics. So the first thing I'm going to do is I'm going to draw myself a graph, okay? And we're going from -5 to infinity. So 1, 2, 3, 4, 5. So this will be -5. And then we'll go 1. It looks like the highest number of x's that they want me to get to is 3. So 1, 2, 3. We'll do a couple more just for good measure. It looks like the highest y value they talk about is 4. So let's go up to 5 or 6. So 1, 2, 3, 4, 5, 6. Call that 6. And then 1, 2, 3, 4, 5, 6. We'll call that -6. And here we go. Let's look at the graph. So let me zoom in a little bit. Okay, so here's what they want me to do. They want me to draw a graph of this function. So let's look at the things that they want me to do. So as x goes to -3 from the left, the function goes to -2. And that is also the value of the function. So this is the point. So the point at -3 is at -2. Okay, so the point at -3 is at -2. And that is the same as the limit where -3 coming in from the left. So I'm just going to draw something random. So we'll start it at 5. It doesn't give me any information about -5. So we'll just kind of come in like this. Okay, and that's arbitrary. It could have come in from the bottom. It could have been a straight line. We don't really know. All I know is that the point at -3 is at -2, and as it approaches -3 from the left, we're going to -2 as well. Okay, let's look at the next part. As we approach -3 from the right, this function should go to infinity. Okay, as we approach -3 from the right, so this is -3, this function should go to infinity. Okay? So this is as we approach -3 from the right. And this could have started up higher. It could have started down lower. All I know is that at -3, we're heading towards infinity. Okay. At 0, we have a point at 0. Okay. And the limit as x goes to 0 is 0. So since this is a general limit, I know that we have to be approaching 0 from the left and the right. Right? Left and right. So as I'm coming into this one, I've got to be going to 0. So let me just kind of connect this. Okay. And then as I leave, I should be connected to this as well. Okay. So before I draw my part where I leave, let me see what else I know. I know, ooh, here's a point. Let me not skip ahead though. I know that as I'm going to 3 from the left, I'm heading to 4. So as I'm going to 3 from the left, 2, 3, 4, I'm heading to 4. So I'm heading here. Okay, I don't know anything in between there, so I'm just going to go ahead and kind of connect this like this. So as I'm heading to 3 from the left, I'm going to 4. As I'm heading to 3 from the right, I'm going to 1. I'm heading to 3 from the right, I'm going to 1. Okay, and then f of 3, the actual point at 3 is at -1. So there's the point. So that means both of these have to be open circled. Okay. And then as I go to infinity, I go to 2. So about 2. Yeah, so it's that horizontal asymptote. So your graph could look something like this. So let's just to recap. As I'm going to -3 from the left, I'm heading to -2. Okay, and that's where the point exists also. As I'm going to -3 from the right, I'm going to infinity. Bloop, yep. At 0, I have a point at 0. Okay, and that's where the limit goes from the left and the right. So left, right hand limit. Okay. As I'm going to 3 from the left, I'm going to 4. Okay. As I'm going to 3 from the right, I'm going to 1. Okay. At the point at 3 is at -1, and the limit at infinity is at 2. Okay, so that's this graph. And again, this graph could look all sorts of different. This could have come all the way down and then come back up. This could have gone up and down and then crazy. But this was my interpretation of these things. So as long as it's got these specific pieces in it, then everything is totally fine. You'll also notice the only point that this would be continuous at that has one of the weird jumps is this one. So this point, the limit from the left, the limit from the right, and the point are equal. So this would be continuous. This one, the limit and the point are the same, but the limit this way is not, so it's not continuous. These two limits are different, even though the point exists. So they might ask you to draw something like that to just kind of see what's happening with a graph. And then in example 12, the summary, they're going to give you a statement, and they're going to want you to see if that statement tells you something about the function, okay? So we're going to have to rely on the rules and the theories that we've just talked about limits, the definitions, to see what we know based on what they've told us, okay? So number one, if the limit as x goes to some value, so some constant c from the left, is equal to the point at c, which is equal to the limit as c to the right, what can be said about the function? Okay, well this is their version of the three-step limit rule, right? So this says the limit exists, right? The limit from the left, the limit from the right. The function exists, and they're equal. So what we can say about the function at c is the function at x equals c is continuous. This is the three-step limit rule, or limit definition is what I would call it. It's not really a rule, okay? This is a three-step definition of the limit. So you've got to be able to recognize it this way and recognize it in our 1, 2, 3 steps. I will tell you in calculus, the 1, 2, 3 steps is going to be how they write it, not so much like this. So this is going to be the shorthand that he writes it in for this pre-calc course. Okay, take a look at 2. If the limit as x goes to the left of the function is equal to the limit as x goes to the right of the function, then the limit in general of the function must exist. Okay, the limit from the left, the limit from the right are equal, then this limit exists. It doesn't say what these are. Normally they would say this one equals L, so this one would equal L also. So these two limits are equal, so this one must exist and be equal to them, and be equal. That would be true also, right? So some form of that, okay? Number 3, the limit as x goes to c from the right does not equal the limit as x goes to c from the, the limit as x goes to c from the left does not equal the limit as x goes to c from the right. Then it has what type of discontinuity? Well, let's think about what's happening. So this limit's coming in here. This limit's coming in here. There's the big gap in between, but it's not an asymptote. Remember, this is called a non-removable jump discontinuity. Okay, a non-removable jump discontinuity. It's important that you get the word jump in there because that's what's happening. It's like you're coming in this way and you jump up there, okay? Jump discontinuity. Number 4, if the limit as x goes to some number from the left is equal to the limit as x goes to some number from the right, but those two do not equal the point, then it has what type of discontinuity? Okay, so we're coming in from the left, coming in from the right, but that is not where the point is. So they want to know what type of discontinuity. This is a removable point discontinuity. A removable point discontinuity. Okay, and again, the emphasis is on point because there's just one point, the point at C, that's in the wrong place. Okay, on number 5, the limit as x goes to c from the left goes to infinity, or the limit as x goes to c from the left goes to negative infinity, or the limit as we go to the right is infinity, or the limit as we go to the right is negative infinity, then what graphical feature do we have? Okay, well, if we're going to the points and we're going to infinity, bloop, right? Or if we're going to negative infinity, or if we're going to infinity or negative infinity, hopefully you see that that's going to create an asymptote, right? So what graphical feature? That graphical feature is a vertical asymptote. okay? So anytime you have the limit at a point that's going to infinity, it is a vertical asymptote. And then the last one, the limit as x goes to infinity, so the limit as we're going to the right goes to some value L, or the limit as x is going to negative infinity goes to some value L. Okay, so as we're going to infinity, we're gonna flatten out and go to L. Or as we're going to negative infinity, we're gonna flatten out and go to some value of L. The fact that these are going to a number at infinity, the graphical feature is a horizontal asymptote. Because they're flattening out and going to a number at infinity, okay? So now you should be able to complete the 2.2 assignment. Let me know if you need any help.